In the last video, we introduced antiderivatives, and so now we want to actually look at another way of communicating that same idea using a different set of notation called integral notation. And so here, recall that this was the general antiderivative that we introduced at the end of the last video. So this is saying that the antiderivative, really, of the function little f of x yields capital F of x plus some constant. So introducing this notation, this whole thing we call the indefinite integral. Indefinite integral. Okay, and within this there's a couple different pieces that we have here. The thing inside this symbol that looks like a curly S, this is what we call the integrand, what we are determining the integral of, essentially, or determining the antiderivative of. And the piece here, this symbol that looks like an elongated S, this is called actually the integral. Okay, and then the dx here, this is really, right now in this module, is not extremely vital, but for notation purposes it is key, because it tells us the variable that we are determining the antiderivative with respect to. In the next module it'll serve a different purpose, but for right now just know that it's a piece of notation that is extremely vital to this mathematical statement. Okay, so whenever you include, or whenever you determine the indefinite integral or write it down, you always do need this bit of information. And so this is read again, the integral of f of x with respect to x is capital F of x plus c, and then you can also say the antiderivative. This indefinite integral will always also result in the general antiderivative, and then again, this we call the general antiderivative. So for example, if I have the function, the integral of 2x to the 2/3, I can determine its antiderivative. Okay, well, remember from the last set of videos, or the last video, we said that we have to increase the exponent by 1. So if I increase that, that becomes 5/2, and then I have a 2 out front. And then I also need to divide by whatever the exponent was, so 5/2, and then add a constant. And just simplifying this a little bit, this is going to be 4/5 x to the 5/2 plus c after I simplify. Alright, so again, same idea, it condenses the notation, condenses the writing a little bit for us. Alright, so now there are a couple different properties of indefinite integrals, just as we had with differentiation, and really these rules stem from differentiation. So if we have a sum or difference of two functions, we can compute their integrals, their indefinite integrals separately, or we're going to talk about definite integrals, same idea. Constant multiple, if we have something times a function, just pull that out and compute the antiderivative as normal. Okay, so for example, if I have this kind of complex function, I can apply these properties one at a time. So I can write this as integral of 4 over 4 over the cube root of x minus the integral 2 pi sine pi x dx, and I should have dx over here too, and then plus integral 4e to the minus 2x dx. Okay, so I just used the sum and difference property. Now I'm going to use the constant multiple property. So let's see, I have 4 integral, and I'm going to write this as x to the minus 1/3. Again, cube root is the 1/3 power. If it's in the denominator, I can move it to the numerator and just make it a negative exponent. Okay, here I'm going to pull out the 2 pi as well. So remember pi is a constant, so now I just have the integral of sine pi x inside. And then finally I'm going to add 4 integral e to the minus 2x dx. Alright, and now this is, let's see, this first one is just a power property. This one is going to be a cosine, and then this one I have to follow the rules for exponentials. So computing the antiderivative, I have 4, and then I'll have x. Now adding 1, I get 2/3, and then I divide that all by 2/3. Subtract 2 pi, and then now this is going to be cosine. Okay, but remember when I differentiated cosine, I have a minus, so that becomes a plus, and then I have to divide by whatever's inside here, whatever constant, or I'm multiplying by, and this should be pi x, I'm sorry. Divide by pi, and then now that's done, and then I have 4 e to the x. The antiderivative of that is just e to the x, and then I have to divide by whatever the constant up here is, and that's minus 2. And now technically for each one of these you would have to add on a constant, but adding up all those constants just results in another constant, so you can just add a constant at the very end. Okay, and now you could leave it like this, but really it's not that hard to simplify it one more step. So going ahead and doing that, let's see, this becomes 6x, this should be thirds, to the 2/3, plus the pi's cancel, so I get 2 cosine of pi x, and then I add to that actually a minus 2 e to the minus 2x plus c, and that will be my general antiderivative. Okay, so again, sum and difference property, constant multiple, and then just simplify. Okay, nothing that should be too surprising, since the properties of integrals follow from, or at least these two follow from properties of differentiation. Okay, the last thing in this module is to do some sort of application with these antiderivatives, so kind of make sense of why we're actually doing this. So here we have a situation where a patient is suffering from headaches. They take acetaminophen, i.e. Tylenol, and we're given information about the rate at which the rate of change of the acetaminophen in their blood, and we want to determine how much is in their blood after 6 hours. Okay, so we're given information about the rate of change, but we're not given information about the actual amount. So what we're given is the rate of change in the concentration, and the rate of change, actually it's in the amount, so I think I'll actually probably use A. So the change in the amount each hour. So we know each hour, let's see, there's 2 bits of information that tells us about the rate. They take 100 grams each hour, and it also decreases by e to the minus 0.25 t each hour. So going ahead and doing this, the amount increases by 100 each hour, but then it decreases by this amount, e to the minus 0.25 times t. Okay, well, if we want to know what a of t is equal to, and I know the rate of change, remember at the beginning of this entire module that we can actually get to the amount of, or we can actually determine the amount of a quantity from its rate of change by using an integral. So if I integrate a prime of t with respect to t, I can actually obtain my function. So this is going to be the integral of 100 minus e to the minus 0.25 t dt. Okay, and going ahead and computing that, I'll have to break it up using the power or the sum and difference property. And so let's see, this will be e to the minus 0.02 or 0.25 t dt, and so this is going to be 100t minus, and now this is going to be e to the minus 0.25 t divided by negative 0.25, and then I have to also remember my constant, and remember that this is all equal to a of t. And so now, just simplifying this, I get 100t, this ends up being plus 4e to the minus 0.25 t plus c. And I'm given one more bit of information. I'm given that they have 500 milligrams in their blood initially. So that means that when t is 0, a of t is, was it 50? 500. So plugging that in, I get 500 is equal to 0 plus 4 times e to the negative 0.025, nope, just 0.25, times 0 plus c, and this ends up being 1, so c is going to end up being 496. Alright, so that means that a of t is now, the entire equation is 100t plus 4e to the minus 0.25 t plus 496. Okay, a lot of work. Last step. We want to know what the amount of acetaminophen in their blood is at after 8 hours. So all I have to do is plug it in. So I have 100 times 8 plus 4e to the minus 0.25 times 8 plus 496. And when you do this computation, you end up getting 1296.5, and this will be in milligrams. Okay, so they have a lot of acetaminophen in their blood, but nevertheless, we were able to go from a rate of change equation to the original equation that describes the amount of acetaminophen in the blood at time t, and then apply initial condition in red here, and then after we got that, we got the function that describes the concentration in their blood at time t, and then determine the amount at time 8. Alright, so kind of a quick use of antiderivatives, and in this video we studied the properties and how to break them up and introduce integral notation too. Okay.